Today we're going to do 2.2b, change in linear and exponential functions. We'll do exponential functions and geometric functions or geometric sequences. So geometric sequences have an exponential relationship because the terms share a common ratio. So, for example, you have an exponential function written in the form of f of x equals y initial, that's an initial term, times r to the power of x minus x1, where r is the common ratio and x1, y1 is a known point. This is for exponential function. Well, in the geometric sequence, you have the formula as g of n equals g of k times r to the power of n minus k, where g of n is the nth term, g of k is a known kth term, r is the common ratio, n is the term number, and k is the term number of the known kth term. So what is the similarity between the geometric and the exponential function? In exponential, we have a common ratio, and geometric as well, there is a common ratio. So that's why there is an exponential relationship, because the terms share a common ratio. That is what we mean by that. And you have r, the ratio raised to n minus k, while the r in exponential is raised to x minus x sub 1. So there is a certain point, but this is about the term. Geometric sequences with a common ratio that is greater than 1, okay, for geometric, with a common ratio greater than 1, can be modeled with exponential growth. So if you try to look at this graph right here, you can see these points, all right? This pertains to the terms for geometric. So that's why you have a sub n is equals to 2 to the power of n minus 1 in this graph right here. Well, the other one, this pertains to exponential function, where f of x is equals to 1/2 times 2, that's the ratio to the power of x. So we're going to look at this later on with these two graphs. When geometric sequences with a common ratio below 0 and 1, a non-inclusive can be modeled an exponential decay. So if you look at the direction of the graph, here, you know it's greater than 1 because it's going up. While here, when the ratio is between 0 and 1, it model an exponential decay. So if you look at the direction of the graph, it goes down, decreasing. This is increasing, and the other one is decreasing. Okay? So for example, you have a sub n equals 32 times r 1/2 to the power of n minus 1, while this f of x is 64 times 1/2 to the power of x. We'll go into the details of this. Geometric sequences with a negative common ratio, this time it's negative common ratio, cannot be used to model an exponential growth or decay. As we can see in this graph, some points are scattered going that way, some points are scattered going down. So it cannot be used to model exponential growth or decay. What's the reason? This is because the base of the exponential factor is function is restricted. The base or constant factor must be greater than 0 but not equal to 1. Geometric sequences, this is for exponential. Well, in geometric sequences can have a negative common ratio, but in exponential function cannot have for exponential, cannot have a negative constant factor. So the explicit rule for geometric sequences, you can have a sub n, it's -2 for the ratio to the power of -1. This is for the geometric sequences. It can have a negative ratio. The domain of any geometric sequences is subset of the integers. Like arithmetic sequences, it can start from 0 to 1. All right, let's have this problem so that we could fully understand what we are talking about. A group of students is working on a project that is due in 6 weeks. To determine how long it will take them to complete the project, they created little tasks that they could do along the way and came up with a total of 324 tasks. They work on the project frequently at the beginning of the month, but had to work on the project later in the month. So the table shows the number of tasks left to complete each week, which can be represented by a geometric sequence. All right, you have the table here. That's the number. N is 1, 2, 3, 4. And the A sub n is 324. These are the number of tasks. And this concerns with week 1, 2, 3, 4. Identify the common ratio. So we can find the common ratio by dividing a term from the previous term. Since we already know that this is a geometric sequence, as it says here, it's geometric sequence, so we can use any of the pair of values of the n values since they are 1 unit apart. Okay, 1 unit apart. So we can choose any of the two values here. So I'm going to choose to get the ratio as 12 divided by 36 because it's more convenient to use. They have a smaller value. So this is equals to 1/3. Of course, we know if we have 36 divided by 108, it will be also equals to 1/3. Okay, so the common ratio here is 1/3. Okay, this is the common ratio. Determine the value of A sub 5. Okay, A sub 5. Using the constant factor found in A, we know that as n increases by 1, here, increase by 1, A sub n decreases by a factor of 1/3. So we can substitute the r, which is equal to 1/3, into the recursive formula. Okay, so what will be our recursive formula here? A sub n is 1/3 times a sub n minus 1. Okay, so that would become, if we have a sub 5, that would be 1/3. A sub n is 5 minus 1. That would be a sub 4. Okay, a sub 4. So we're gonna look for that. 5 minus 1 is 4. So what is our a sub 4 from the table? We have 12. So a sub 5 will be 12 divided 12 over 3. That is equals to 4. So if we have 5 here, this will be equals to 4. That's it. Or you could say the fifth term is 4. So there are 4 tasks to answer the question. There are 4 tasks left to complete the project. To complete the, let's say, to complete the 5th week. All right. Let's try to compare linear and exponential functions, because in the previous video we were talking about the similarity of linear and exponential functions, but this time we will be comparing the linear and exponential functions, comparing the two. So the characteristics or key features of a function includes the following: the domain and range, the x and y intercepts, maximum or minimum values. We have rate of change over specific intervals, the end behavior, positive or negative intervals, increasing or decreasing intervals. These are the characteristics that we have to consider. Right. By using the key features to compare the linear and exponential function, we could say that many of the features are similar, but the rates of change are different, because the linear function has a constant rate of change, while the exponential function has a constant percent rate of change. What do we mean by that? For linear, we are adding the same number to each output of a linear function, while in exponential, we are multiplying the same number to each output of the exponential function. Okay, so this means that multiplication, but we are multiplying the same number to the exponential function. So multiplication grows faster than addition. So a quantity is increasing exponentially will always exceed in the quantity increasing linearly. So in other words, the quantity in the linear function is less than the exponential function, because when multiplying the exponential, it grows faster. So multiplying the same number is faster in growth, okay, compared to the linear function. So let's have an example. Consider the two functions below using the graph. Okay? So it's very clear that we are looking here a linear function, right? Since we can see in the graph that it forms a line, but in the second one we form a curve that is going up. So maybe we could describe this as exponential function, because there are two types of, looking at the graph in exponential, whether it's growth or decay. State the x-intercept of each function. Okay, we need to look at both the graph of the function. So I'll start with the linear function. State the intercepts. So what are the intercepts? The x-intercepts, okay, and the y-intercept. Of course, when we look at a linear, we could easily see this point right here, it intersects at x, and this point right here, it intersects at y. How about in the exponential, where we can see it intersects at x as well, and we can see it intersects at y as well. So both function has x and y intercept. So the x-intercept in both function is found here at 0, 0, 1. 1, 0. Sorry for that. This is 1, 0. And the y-intercept is at 0, negative 1. Same thing here. The y-intercept as 0, negative 1. And this x-intercept is at 1, 0. So that means the x-intercept is at 1, 0. I always miss out this one. X is at 1, 0. And the y-intercept is at 0, negative 1. All right. Let's have the question B. Compare the end behavior of the two functions. So we are looking at the end behavior of the two functions. All right, let's do this. I'm going to assign the end behavior. This one right here goes to, I'm going to move this. So I'm going to write the linear function here. Okay. Going to the right, as x approaches positive infinity. Going up here, as y approaches positive infinity. Well, on the left side, this is the left. X now approaches a negative infinity. Going that way. Going down, y approaches a negative infinity. All right. How about the exponential? All right, let's look at the graph. At the far end, this x here approaches positive infinity, and going up, the y approaches positive infinity. While this here, if you look at it, curves that way. Okay, the graph curves that way. That means as we move towards the left, x approaches a negative infinity, and y, what's the y approaches a negative infinity. All right. As y approaches to, oh, I forgot. Sorry for that. It's not negative infinity, but we could use the asymptote. All right. So y approaches a negative 2. So it's the difference of the 2 right here. All right. So on the other side, and closer to y is negative 2 as x gets further from 0 on the left side. So that is x approach a negative infinity and y approach a negative 2 for g of x. All right. Using the graph of each function, this is comparing the end behavior. But I need to, all right, I'm gonna write. So here on the linear function, on the left side, as f of the function of x takes larger and larger negative values as x farther from 0. So that means takes become bigger and bigger, or larger and larger negative values going to negative infinity as x gets farther from 0. From 0. So that is, how are we gonna describe that? As x approaches negative infinity, y also approaches negative infinity for the function of x. So both on the right side, they are the same, but they differentiate only on the left side. So on the other one, this is the exponential function. Okay, exponential function. As the values of g of x get closer, okay, the values of g of x, this is for exponential, get closer and closer to y, what happened to y? It will become negative 2 right here. As the x approach to negative infinity, it gets closer to y as y approaches to negative 2. Okay, y negative 2 as x gets farther. Farther away, farther from 0. on the left side. Okay, farther from 0 on the left side. We are only talking on the left because the right side, the exponential and the linear function are, their end behavior are the same. And that is as x approaches negative infinity, y approaches negative 2 for the g of x is for the exponential function. This is the g of x here. This is the function of x for this graph. Okay. Using the graph of each function, find where f of x would be equals to g of x. So if we're just transferring what's going on. If we do this in the calculator by graphing, this is what happened. And you can see how the graph looks like in a calculator. We can see at this point here, since their x-intercept are both 1, 0, and the y-intercept are both 0, negative 1. Okay, so this is what happened, is that we can see that the two functions intersect in the x at x, or at 0, negative 1 for y intercept, and 1, 0 for x. Okay, so this means, what does this mean? That at x equals 0 and x equals 1, the two functions are equal to each other. Okay, they are equal. And it happened at this point, at x equals 0 and x equals 1. Alright, that is how we do, or how we know where the f of x and g of x are equal. Compare the average rate of change for each function over the following intervals. So you are given an interval of negative 1 to 0, 0 to 1, and 1 to 2. So with that interval. So maybe we can do that by calculating the average rate of change with the formula. Remember, we did that using the average rate of change. When we did the average rate of change, we did the f of b minus f of a over b minus a. That's the location. Okay, so let's look at this graph right here. With the intervals of when x is negative 1 to 0, intervals right here, negative 1 to 0. So you can see this interval, this right here. So we can use for linear function, okay, so we can have, since it's 0 and negative 1 to 0, So f of 0 minus f of 1 over 0 minus -1. All right. So this would be equals to -1 minus -2 over 0 plus 1, it's equals to 1. So -1 plus 2, it's 1 over 1. So the value there, the rate of change there is 1. So from the interval of 0 to 1, okay, the range 0 to 1 is from here to here. So before we did -1 to 0, right? So for that interval, we have f of 1 minus f of 0 over 1 minus 0. So 0 minus -1 over 1. So we still have the rate of change as 1. For the interval of 1 to 2, so from here 1 to 2, so we have f of 2 minus f of 1 over, when it's 2, it's 2, right? So 2 minus 1. Okay, 1 minus 0 over 1, the rate of change is 1. So the average rate of change in linear for linear, it's constant, which the value is equal to 1. So the values are increasing are increasing by 1 each time. That is how we understand that. Okay, let's look at the exponential. Doing the same thing for exponential. So when it's f of 0 is 0. So I have the interval. Okay, let me do the interval here. -1, 0. Okay, so when I have -1 to 0 here, so what do I have here? This is for, I'm gonna write here for exponential. I think I'm gonna use a space to differentiate. For exponential, right? So the first interval is from -1 to 0. All right. So f of 0 minus f of -1, we're trying to get the rate of change. So when it's 0, it's 0. A -1, we have a -1. Yeah. So what we have when it's 0, it's -1 minus When it's 1, it's negative 1.5 right here and right here. This is negative 1.5. This is negative 1. So that's the difference between the two. And 0 plus 1, it's 1. So you have 0.5 over 1, it's equals to 0.5. So the next interval is from, what's the next? 0 to 1. So we're going to have f of 1 minus f of 0 over 1 minus 0. So the f of 1, okay, right here. So f of 1, it is 0. Then f of 0, it's negative 1 over 1. So it's 1, right? This time it is from 1 to 2, right? 1 to 2 interval. So f of 2 minus f of 1 over 2 minus 1. All right, for the, okay, so 2 minus f of 2 is 2 right here, minus 0, and then 2 minus 1, it's equals to 1. So we have the rate of change of 2. So what can you say about our rate of change here? It is increasing. So although exponential function is increasing faster, faster, it should be in exponential function is increasing faster compared to faster rate compared to linear. Linear is also increasing, but here linear is constant function. So both are increasing. It can be increasing, but the linear has a constant. All right, that is what we have observed by looking at, the rate of change is our basis for doing that. Okay, let's have another problem right here. Consider the function shown in the graph on the table below. So we have, of course, this is linear. We can see it is linear because the graph form a linear. So this is a linear function. And we'll try to check on the table whether it's linear or exponential. But the way we see on the g of x, this is an exponential. But we have to check and how the graph would be. State whether its function is linear or exponential. So we can, as I've said, we can see in the graph the f of x. This is f of x. The graph is a straight line. So from the table, we saw a differences of ratios of outputs to determine. So we can start by finding the difference in the output here. Let's say I'm going to do it here. The difference that so I will start with 0.512. When I say difference, minus 0.4096. So the difference is 0.1024. If I do a 0.64 minus 0.512, I come up with a 0.128. I will have to do one more. 0.8 minus a 0.64. I'll have a 0.16. So this is not a common difference. So in other words, this function is not linear because the difference is not common. Even though we proceed and so on and so forth, still it's not common. But let's do the ratio. About doing the ratio, like 0.512, we get the ratio divided by 0.4096. By using the calculator, we have a 1.25. How about doing 0.64? We divide by 0.512. We come up with 1.25. We'll do one more. About 0.8 divided by 0.64. We come up with 1.25. Since the output has a common ratio, then we could say this g of x is exponential because they have a common ratio, and the ratio is 1.25. Okay, so therefore this is exponential. As f of x increases by a constant amount, it is linear if it increases by a constant ratio. So compare the intervals where the function is increasing or decreasing function. Since the f of x is linear, we know it only increase or decrease over its domain. So we can determine whether f of x is increasing or decreasing by looking at the graph. So by looking at the graph here and looking at the domain, let's say when x is -4, the domain is, when x is -4, the y is equals to 1. When x, let's say some certain point here, when x is 4, the value is 2. So the f of x is increasing or decreasing by looking at the graph here. And it's very clear that it is increasing. At the same thing in the exponential function, only increase or decrease over its domain. So we can determine whether g of x is increasing or decreasing by looking at the outputs in the table. So looking at the end behavior of the graph, we can see that y-intercepts in the f of x. We can see that the y values are growing or increasing as x increases. like this. I said if x is negative 4, y is 1. As x increase, let's say x is 4 right here, y is 7. That is what we mean as y are growing as x increases. Okay? Looking at the function of the outputs of the table in g of x, the values are getting larger. Okay, getting larger as x increases, and it increase faster. Both, so we could say that both function are increasing. You know, when let's say in AP Precalc exam, if you are given questions like this, write as much as possible you can write and try to describe everything you can describe regarding what is asked in the question. Okay? Think about the term that they are wanting, like increasing, decreasing. So say about how the graph increase and how the graph decrease. Determine which function will have a higher value as x increases. So we already know that f of x increases linearly. Okay? When you say f of x increase according to how linear it is. Okay? That is what we mean by linearly. If you can see, it's very visible. It is going up. But in g of x increases, how does it increase? We're talking about g of x here. And this is f of x. So increases exponentially. Since this is g of x is an exponential function. So we can use what we know about the rates of change of linear and exponential function to determine which one will exceed the other. So f of x will grow by a constant amount. Okay, constant amount. While the g of x it grows faster since it's multiplied. So it grow by a constant percentage. So g of x, we could say, g of x will have because it's according to percentage. So g of x will have a higher value as x increases. So if we look at the graph right here, using, if you use a graphing calculator, this is how it appears. So in other words, you look at how in this graph right here, since our domain is up to this point, maybe at 16, since this is by 2. So let's assume, but look at how fast it grows. The g of x increases as x increases. Okay? All right. I think this answers the question. All right. We'll have more about linear and exponential function, um, that is arithmetic and geometric function, in the next video when we do the problems and solutions. All right. So let me say this: if I can do it, so can you. So don't forget to hit the like button and subscribe